Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Industry Partner Series, Managing Design Risk for Retaining Structures. My name is Megan Purdy and I'll be your moderator. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the countries throughout Australia and recognise their continuing connection to land, waters, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous cultures on Earth and our first engineers. We pay our respect to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's event is being hosted with Engineers Australia's industry partner, Brickworks. Brickworks is a leading global building materials company with a proud Australian heritage dating back to 1934. They design and manufacture high-quality bricks, pavers, roofing and masonry products that shape enduring, sustainable built environments across Australia, North America and beyond. We thank Brickworks for their continued support. Now we'll hear from our three speakers, followed by our live audience Q&A. So I encourage you all to send your questions through to the speakers via the chat box. I now have the opportunity to introduce our first speaker, Tan Ching. Tan, the founder of CMT Engineers, brings a wealth of experience in civil, structural and geotechnical engineering to the table. A graduate of a prestigious engineering institution, he has honed his diverse skill set through projects across both Asia and Australia. Tan's leadership extends beyond design. His experience navigating local councils ensure projects are completed on time and to the highest standards. Please join me in welcoming Tan Ching.
Good afternoon and greetings to all viewers. Welcome to the webinar hosted by Institution of Engineers Australia with the industry partners Brickworks, CMT Engineers and JoeWitt. Today's topic will be managing design risk for retaining wall. My name is Ching Ming Tan, the founder of CMT Engineers, and I will be speaking on the first part of this webinar. Let me run through the types of retaining wall that's out in the industry. The definition of retaining wall is a structure designed to retain any open cut surface and material that require to be held back in a long-term stable condition. There are two types of wall. One is a gravity wall, and the next type of wall is called embedded wall. What's the difference between these two types of wall? The difference between the two types of wall is a gravity wall retains any type of material and the foundations are shallow and sits on a soil and is called a gravity wall. It is just on the ground. The foundation is just slightly on the ground or slightly below the ground. Whereas in embedded wall, it is a relatively thin wall, thin steel structures, timber, and any material which form part of the foundation. And the foundation is anchored deep into the soil. So that's the difference between two of them. One, the foundation is shallow. The other is deep into the soil. Now, that's a couple of pictures here showing types of gravity walls that's been widely used in the industry. I've shown 5 types of gravity wall. One is called a masonry wall. It is actually a block wall, which is hollow. And when it is built, you actually fill it with concrete and steel reinforcement. The next one is called a reinforced wall. It is commonly used in bridge abutment. And the disadvantage of this wall is that it's got geogrid and tie-back reinforcement right behind the precast concrete panel of that reinforced wall that relies on the backfill material for friction to hold the wall. The next picture is a stone wall. It actually can be a sandstone block cut in size, or it can be cobblestone or large boulders built up as a mass gravity wall. The other one is wall is normally called a concrete wall. It actually consists of precast units, which are stacked up and assembled up into a height to retain the soil, and is infilled with road-based material, which form part of a mass gravity wall. The last of it is the concrete reinforced wall, which is conventionally is a design wall, a custom design wall, where you design based on the height, the soil foundation, and is a concrete reinforced wall, which you got steel reinforcement and a concrete forming part of the wall. The next type of wall that I will be speaking on is types of embedded walls. It's called a cantilever king post. Now, remember, there's many types of embedded walls. One commonly used in all the greenfield and infill projects in Australia, and especially in Queensland, is using steel posts and concrete panels. The post is called a king post, and the panels are called leggings. They are actually holding back the soil, and all the loads on the panel are then transferred to the post. And the posts are in deep piers, which is below the ground. In this photograph, the first photograph is a wall that I have done quite some years ago. It's about 4.6 meter high, and that's a large wall that's in the subdivision project. However, the design of cantilever king post has limitation. As it goes higher and higher, serviceability becomes an issue, and the ground foundation, it becomes very large and becomes uneconomical to build. And the other picture is normal timber lock and timber legging used for low wall, very commonly used in the last 20 to 30 years ago for subdivision. And it's only since after 2007, I believe, that concrete panels then start to be used to replace this timber king post. The other slide is commonly now being used in large subdivision, which is king post, low level, probably about 1.6, with a fence as a common boundary, sitting on a slipper wall, king post. This is a picture of a king post, which has post tension. You will notice that the post has been tied back with post tension on the top and the bottom to hold it back. Normally, this is used when a serviceability becomes an issue, or due to high surcharge load that you want to control deflection. The other picture is called a tier king post wall. It's actually a tier wall separated by a distance. Normally, the separation of the distance is quite far apart, where you try to design it in such a way that the upper wall will be so independent design, and the bottom wall will be independent design. But when the wall separation is minimal, it becomes very complex, because there is a interaction between the passive and the active pressure in the separation. If the separation distance is minimal, normally we will use a soil structure interaction program to do the analysis, and this is normally carried out by a geotechnical engineer. However, if you do not have the program of the soil structure interaction, what I would normally do is to treat the upper wall as the first line of defense to protect the property upstream, and the height of the wall will be the top of the wall right to the base of the ground. and the second wall at the lower will be treated just like a normal wall. Therefore, in any situation, if the lower wall is removed or damaged, the upper wall is still intact and is still protecting the upper stream property. Another type of embedded wall, sheet piles, very commonly used for shoring temporary work excavation. Not for deep basement excavation because it becomes too not economical and due to deflection. However, there are cases where you can still use sheet pile and with post tensioning and with railers and struts. The next picture below is a concrete slipper, a concrete sheet pile that is used for rehabilitation work in river. When steel sheet pile is a problematic material due to durability, concrete sheet piles can be used. These are all basically cantilever design embedded wall. Another type of embedded wall, contiguous wall piles. Piles that use drilling, piles constructed by drilling rigs, where they are drilled below the ground next to each other, and then they are excavated, expose their surface, and is basically a cantilever embedded wall design, widely used in construction of basement of buildings. The next picture is a picture of contiguous wall piles that you can see that is being used to hold a road embankment, where road works are being done below the toe of the piles. Another type of embedded piles, and I wouldn't call piles, embedded wall, is using secant piles. You can see from the schematic diagram is actually piles intersecting each other. Very widely used in deep excavation, where you want to prevent water from coming from the basement. They are used in buildings, especially deep buildings. If I'm not mistaken, I think the Queen's Wharf project in Brisbane was using secant pile or diaphragm wall. Here you are, diaphragm wall, very commonly used. Involves a machine called cutters, where you remove the soil and then you put reinforcement cage in, and you put and you pour the concrete in there to form a wall. And it's widely used for underground railway station, where station walls are all using diaphragm wall. Okay, let's see what the current AS4678 2002 says anyway. In the current code of the AS4678, there is no section or any design on embedded wall. Please take note, because there is a lot of king post wall, especially for brownfield and infill jobs, projects, where designers are designing embedded wall and they are not using the right formula. The only reference that's in AS4678 on piles or posts under lateral load is the Breach, Hansen, and the Brom's method used in the design. And that is in accordance to the piling code. The design of an embedded wall uses a theory called limit equilibrium method, and this analysis is ultimate limit state. This formula has been around since in this last 24 years, and is widely used for all embedded wall design in large projects. However, AS4678 has no reference to that LEM method. The difference between LEM method and Brons and Brinch-Hansen is due to the presence of unequal pressure acting on the structure, which form part of structures are below into the ground. So it's a totally different set of calculation and methodology, where Brons-Brinch-Hansen is just a lateral load, not due to pressure, but a lateral load that is acting on the pile, whereas the LEM is actually a set of calculation which is due to the difference of soil pressure that causes a loading onto the structures. Now, the LEM method considers the driving forces from the active pressures, while the resistant forces derive from the passive pressures, and they are always in equilibrium. So it's a determinate structure which you can solve by using mathematical equation. How do we mitigate design risk from a designer's point of view? I have listed here a couple of points there. We'll start with the first one. As a designer, we've got to make sure that we get the right soil investigation and choose the soil parameters value. I have personally seen that king post design being using a site classification report to design a king post. Sometimes it's really amazed me how a site classification is for a building can be used to design for a wall. So my advice to designer is please do a soil investigation and get the soil parameters, because these are the values are needed to design your LEM. LEM depends on effective apparent cohesion value and also the angle of frictions and the soil density. The next point is, when you design the wall as a designer, we have to mitigate the risk to know that whether there's going to be any construction loading down the road. I'll give you an example that a wall that has been built without taking any consideration of any construction loading, because down the road, a year later, they decided to build a house. And the next thing, there's a concrete truck next to the wall, pouring concrete for the house slab. And guess what? The wall moves. The next point is material strength reduction value adopted in your calculation. These are the 5G. They are all the material factors, which is favorable and unfavorable, which you can obtain from the AS4678. And as a designer, you got to make sure you use the right figure and the right reduction factors. Next point, methodology and formula. So use the right formula. LEM has never been for AS4678. So sometimes I wonder those structural engineers who do a lot of infill and brownfield, what sort of formula do they use? Next point, when you are a designer, always make sure that when you design a wall, look at the surrounding features, terrain, and landform within the wall. You have to ask a question whether there is any grass swale, a creek, or a landscape pond, or a biopond or retention pond next to the toe of the wall. Because with the presence of water, it does make the foundation of the wall weak because of the presence of the water and the soil value changes. All these consideration as a designer needs to be taken so that you can mitigate this risk. So look at the drawings that is being issued to you by the civil engineers. Look at it, the whole entire layout, and make sure that all the environmental factors that can influence the design of the wall are considered. Next is flooding and overland flow path over the wall. Very common failure that I've come across. There will be two examples I will show you in later down the slide. Next one is unplanned excavation. Think about all the services, accidental excavation, swimming pools. All this should be considered by the designer. The other one is the communication between the three disciplines of engineers. A common miscommunication I noticed in all wall design. The civil will do his own things. The geotechnical will just do his part on the foundation. The structure will just design what is given to him, the forces by the geotechnical. We have to take note that a wall is not a piecemeal design. It is a comprehensive design that consists of a civil, geotechnical, and structural engineer. It's not a piecemeal. Because a wall fails, and if it's considered a piecemeal, right, at the end of the day, the person who is going to suffer is the client, because the geotechnical guy will just say, no, it's not his fault. The engineer, the civil guy say it's not his problem, it's the structural, and the structural say that I was given a value by the geotechnical to design. So bear in mind that a wall design is never a single discipline, engineering discipline. It's a three discipline. And make sure you do a site investigation, a site inspection where you want to, where the wall is to be built. Most designer, they never go out. They will just pick it up from the drawing and just design it, and without looking at the site condition. A typical example, I will show you what goes wrong. A real life project down in Brisbane, a stormwater at the toe of the wall. Did the civil engineer thought about the wall? Did the wall designer thought about the stormwater? And guess what happened? The wall moves. That's a real life project. The wall actually moves. Now, whose responsibility? Overland flow path. See the upstream, see the behind the wall? It's a big patch of open space, and water was just sheeting, flowing down, and it wasn't taken into account in the design. It's a very good example when you design a wall. Think about sheet flow, and the structural and the geotechnical. You just got to highlight to the civil engineer and inform that water is always the culprit of wall failure, and is the water that's sheeting from behind it being captured and diverted. These are all the risks that can be mitigated as a designer. Another wall failure, this is due to embedment depth not insufficient. This up in Queensland, same issue. See the tier wall, they're quite separated away. So the wall are actually designed separately, but there's insufficient embedment depth, and that's started to move. The next example, see the clouded area there? There's a gap there. The panels are popping up because the big post is moving forward, and the bearing that where the panel is relying, where the concrete panel is sitting onto that the second post, right, has moved out and it started to pop up. That's a deflection problem, a serviceability problem. And in normal LEM method, when you do a calculation, you have to do two parts of the calculation. One is the LEM method, you find the embedment depth. And then the next part is to find the serviceability, which you normally use a soil structure interaction to find out the deflection on the piers and the posts. This was taken in Brisbane. The top wall was a slipper wall using timber, and down was, second tier was Boulder's gravity wall. See the big gap under the the slipper wall? That's where water is coming down. The design will stand by itself, but it just happened that there was a big downpour, heavy rainfall, and water find its way to the weakest point, and it just undermined the foundation. A typical good example for civil engineer, when you do site stormwater drainage next to a wall, please do consider to divert your water and capture your water away from the wall, or design for the surface water. This is one wall that totally failed in Sunshine Coast. There is a stormwater pit behind there. We do not know whether is it due to leaking from the stormwater, but however, the next slide will tell you exactly what's going on. You can see the wall at the far end there. The fence are all not in straight line. They are buckling, and some of the wall has been pushed up. There you are. That's the top of the wall, and you can see all the tension crack there. So what is actually has happened is there is a slip failure there. The slip failure has causes the wall to push down. And next to the wall was a house on screw piers, and the whole land had subsidized and separated out from the house foundation. There you are. You can see the house being sitting in the original position, and the land has subsidized. When you design an embedded wall, always be cautious that if a wall is not being built on a slope area and is holding field, which is is holding a field sitting on a slope, just be cautious that a slope stability analysis needs to be undertaken. And it's just not just designing the wall itself that it's standing. My next mitigation of design risk in the point of as a point from a builder. As a builder, when you build, just make sure that your material compliance are met anyway. Especially steel posts, you know. Check the steel mill certificate whether they are ESPO ACRS or not. Because steel section coming from overseas are different from steel section manufactured in Australia. Just be cautious about it. Even you might have a mill certificate produced from overseas, it is not exactly the same as what is in Australia. They have noted, because their grading is totally different anyway. Next one is make sure you test or carry out on the piers. And how do you vibrate the piers if it's too deep? What sort of concrete are you using, you know? Are you using trimmy concrete? Are you using trimmy pipes being used? I know trimmy pipes and trimmy concrete are being used for large scale project, which has deep holes. But bear in mind that these are good practices, because you want to ensure that the concrete are fully compacted and not segregated. The next point is how a builder can assist a designer to mitigate risk. If you drill a normal ground and you encounter soft ground, which is different from what is from other holes that you have built, that you have drilled down just upstream or downstream, think carefully whether, you know, the hose is going to be collapsed or not, or how are you going to prevent the collapse? These are all the things that you can help a designer to mitigate risk. It is actually a construction methodology. For small little infill jobs, 1 meter up to 2 meters, I know a lot of people don't use casing. They normally use forms. They buy circular form and try to hold back the holes from collapsing. But bearing in mind that at the end of the day is the quality of the piers that are very important that will help to mitigate the design risk. Laying out subsoil pipe and grade is also a challenge behind the embedded wall in king post. You can't get it right. Therefore, we just got to try to see how we can do it properly. Well, what I've done is normally is I'll make sure I'll put a plastic sheet or some sort of impermeable membrane on the ground before I lay the subsoil pipe. So in case there's any stagnation of water is trapped within the plastic sheets or any impermeable material, so it will not soak right in contact with the soil, causing this soil strength to be lost at the top of the pier head. Material backfill behind the wall is very important for stability. The methodology of construction can reduce the wall failure. There's many ways of doing a backfill. You can backfill by using hang compactor, or you can over backfill and compacted it up to the required compaction, and then use an excavator to trim it back, and then you can then put in your backfill, your filter material behind it. So understanding the sequence of the construction of the wall is very important. And there's no difference between doing a small job and a large job, because the design philosophy doesn't change. The only difference between the big job and the small job as a builder is the use of machinery. That's another wall failure. It was built for about 20 years down the road. The owner came to me and said that the wall is failing. What can I do? And he said there's Form 15 and Form 16 certification. Was approved by council. I assisted him to write a report and did some testing on the timber material and to check whether it's compliance. A two-tier wall failure. That's right in Brisbane. Acoustic fence on top of the upper wall. Separation between upper wall and lower wall is minimum. Panels drop off. It tells you that the post has failed. And that means the embedded piles or piers below the ground has all moved and causes dislodgement of the panels. A typical design in a clouded area showing some design work, then some construction work, patch-up work for wall in a large subdivision. That's the blow up of the area, and see how the whole panel and the post is being held by just by a piece of reinforcement rod. That's real life. That's happening out there, really happening out there. And engineers who inspected the wall sign it off, and it's shocking. All right, next, ship pile movement. Yep, that was down in Brisbane. Whole entire ship pile move. Sewage pipe right behind that building there all was dislocated. It was a basement excavation using ship pile. That's 100% failure due to movement and toe embedment, not enough, insufficient. An overland flow path. Imagine how strong the impact of water energy causing a dislodgement of a concrete slipper wall. It's not the geotechnical or the structural engineer fault, but I'll put it onto the civil engineer for not being able to see the impact of surface water. In the AS 4678 next amendment, there will be some sort of cutoff drain in one of the chapter that the civil engineer will have to design to capture the overland flow path if there is, or any on-site stormwater. So take note, slipper wall or embedded wall, any gravity wall, the design is not just solely on a geotechnical or structural engineer's responsibility. It is also a civil engineer responsibility. It is a complete system consisting of 3 disciplines. So if you get a Form 15 and Form 16 signed off, just make sure that it covers the drainage part. And if there's a failure, and if you come around and say, I did not cover, drainage is not my design, well, the person who is going to be responsible is the civil engineer. You drew the wall on your plan, on your civil plan. Have you taken account of the storm water or surface water flowing to your wall? AS 4678-2002 now. The next amendment is due. It's about to be due anyway. In section 1, it says that wall has to be engineered and designed to AS 4678 if it is more or equal to 800 above. And I'll give you a little bit of history about the AS 4678-2002. When AS 4672-2002 was published 25 years ago, with only one amendment in year 2003, the building code, or the national code as it's now known, has never had any compliance reference on design retaining wall, which is classified as a 10B. This means a retaining wall, right, engineered, right, has no any performance standard to gauge with. It was in only 2019, NCC decided to publish a section on retaining wall design and make reference to AS 4678-2002. So that's an extract from the NCC code. So what does it tell us? So this is what it means. It says that prior before AS 4678-2002, any design of retaining wall, be it a large project or a small project, there is no code in the design for that any retaining wall at all. The engineer is responsible for his own design and using his own design criteria set in the design. When AS 4678-2002 was published, then all wall from then onwards will have to design as per the code. And that is the reference for wall design where every engineer will use, are using it now. But as I said before, 2019, there was no reference in the building code at all. Until 2019, NCC decided to put in a code to say that, hey, it's a 10B classification. It is now needs a performance standard. So the AS 4678 is the measuring tools to measure the performance of the wall. Each state has its own building act, which cross-reference the building regulation and the NCC code. In QLD, the building regulation refer to wall needing approval for 1 meter or above. So that means a building certifier is required, okay? So wall that's less than 800, you do not need any design at all. But the moment the wall is more than 800, you need a design. You need an engineer to do a design, but it does not trigger the Queensland Building Code because it's still less than 1 meter. The moment it hits more than 1 meter, the building certifier is needed as to meet regulation. My next presentation is mainly more to local authority viewers. If you are viewing this webinar, it will be helpful for you to help how you mitigate design risks in designing of retaining wall. A risk management of wall design can be further mitigated based on the following. If the regulating approval authority does the vetting and approval of the drawings, ensuring wall design comply to legislation and code, this means that the local authority needs to ensure plans and certification meets compliance. And this is where assessment engineer comes in council or in a regulating body. This is where you play a role to ensure that the drawings or the design calculation meets the standard of requirement. It is assessment engineers must know exactly how to assess the documents, all right? And you don't need to be to understand the calculation, but there are a few things that you need to look at while you're doing the assessment of the drawing. Okay, so this is where the assessment engineer comes in. In a development stage where you get a big project and you assess the assessment of the layout, the engineering concept, these are a couple of questions that you always have to ask while vetting the drawings. Here are a couple of points. Points like, is the wall building on that location the only solution? Do you need to fill that high? Or is there any other way? Are the height of the small wall, right? Are they bound at the boundary, or is in the upper wall or the lower wall? Is there any flow path coming down behind the wall? Is the design platform created to allow a new flow path into the wall? This is an example where you build a wall on a natural surface flow path or a natural surface water flow path. You know, you don't want to do that. That's creating risk. You know, if there is an upstream catchment coming down and you can't avoid it, well, have you thought about the drainage? Has the drainage been calculated? Has the drainage been designed right behind the wall to capture that? And what's the stormwater event that is needed to calculate? Is subsoil pipe drainage laid in a lawful point of discharge, and has it been identified? Is there any landscape behind the wall? These are all things that will influence the performance of the wall. Any catchment drain on top of the wall? Is there any services there? Can it be avoided? What type of wall? Is it a tier wall? Is it a concrete sleeper wall? Is it a block wall? A wall will determine the stability, and the type of wall is very important. How you design. It doesn't needs to be a sleeper wall. It can be any wall. It can be a block wall too, anyway. And has global stability been considered or not? Where's the wall boundary location? Is it upstream, downstream, in the middle? If it's in the middle, does council allow the a covenant in the title to say that the wall is being shared by upstream and downstream? Where are the services located next to the wall? Any future digging near the wall, or is there any maintenance to the wall allowed in the design? Is it a council assets or a private asset? Council assets normally is 100 years. Look at the design of the wall, look at the material, durability. types of wall? Is it easy to maintain, or does the wall suit the terrain? And what about the replacement of the wall in the ends of its at the end of the design life? Is there any access to it? You know, and especially wall built next to biopond or retention pond. Sleeper wall is not 100% waterproof. Water can migrate behind the wall. Okay, and that backfill behind the wall, the soil are all saturated. So is it stable? Is it suitable? And zero boundary wall building built right to the property boundary. What's allowable for the wall to go up? You know, that's supporting the building. That's part of it. You have to think about it. Drainage design for surface flow and overland flow path, how you mitigate it. So when it comes to operational work, that's where you do your detailed checking. You make sure that soil investigation reports are given and what are the types of testing, not site classification. All right, that's not right anyway. Was there any global stability undertaken? Next question, did the structural and geotechnical drawings form part of the project consultant, not piecemeal? You got to make sure the design of the wall by the geotechnical and the structural are incorporated in the civil set so that you get a complete set. You have track records and you have records on the documents. The wall products, if we are using a wall product to form a wall system, is it approved? Is it approved by the building code? In the building code, does it meet the fire rating? And the next thing is check the Form 15, make sure there's no exclusion, very common. The structural engineer will say that he's designed the wall, but exclude geotechnical. The civil guy will not even do any Form 15 for retaining wall because he says he's not involved in drainage. So who is involved in drainage? The drainage component of a wall system is totally left out. This is happening out in the industry. Form 16. Make sure it includes all the discipline. Everyone goes out and do the inspection. So the civil engineer got to go out and make sure the catch drain behind the wall or the permeable backfill material meets the specification. Subsoil pipes are laid properly. And inspection, that's the most important, how you define inspection. Well, as for a council inspector, when you go out, we don't really expect you to measure all the holes and identify the structure size and all that. What you are inspecting is basically things that are related to council. So all you got to make sure that there are sufficient design, right, adequate to mitigate that risk, and that all assets that belongs to council are properly protected. And you do not want a stormwater pipe that's hugging next to a wall and the assets belongs to the council, and if the pipe breaks, the wall start collapsing. As constructed plan, yep, a very good exercise, things that the council should take note. Make sure that currently I haven't seen any as constructed plans on walls being built yet, but it will be good if as constructed plans for wall be taken, be identified, especially levels, as it will be useful for track records. If there's any wall movement, this should be kept. Compaction test of backfill, this should be also noted that it should be given to the assessment engineer and certified by the design engineer. And the next is the builder is building the walls. Make sure it's qualified. I have come across recently where a builder was building a 1.6 meter high king post wall, and the owner came around calling me and I have concrete poured into the piers all halfway. And the next concrete coming in is tomorrow. And I asked, is he a qualified builder? Has he got a QBCC license? And he said, no. The reason I chose him because he was cheap. And he said he can do the wall. Well, take note that all walls need expertise to build. You don't need DIY builders. Next is check your Form 15 and 16 to ensure that all compliance to the codes are referred. And I've seen Form 15 being referred to AS to the footing code. And I still can't understand how does it refer to the footing code anyway, right? And take note that all walls is a tree discipline. A tree discipline forms a system, and the final system is a wall. It is the civil, the structural, and geotechnical engineer. Well, thank you for listening to my webinar. And my quote of the day is, a sound wall design integrates the contribution of three engineering disciplines, civil, geotechnical, and structural, to produce a wall system that satisfies its design intent and performance requirement. All right, thank you very much. And I hope you enjoy the next webinar, which will be presented by Dr. Kai Ming. He is an expert in embedded wall. He will show you the whole theory of LEM calculation and the difference between Bridge Hansons and Brom, and he will also give you the actual requirement, the actual need to make sure the wall is safely designed, especially for embedded wall, cantilever wall. Thank you very much.
Thank you, Tan, for your input today. I now have the pleasure to welcome our second speaker, Dr. Min Tsai. Dr. Tsai is a highly experienced geotechnical engineer with over 30 years of postgraduate expertise, contributing to major tunnelling and infrastructure projects across Southeast Asia and Australia. His experience spans roads, rails, tunnels, bridges, and soft ground treatment solutions. He has held key lead roles in significant Queensland projects, including the lead geotechnical team leader for the Bruce Highway Upgrade, CSSIW, and the Coomera Connection Connector Project. Dr. Tsai is currently a director of GeoWit, specialising in geotechnical software development, and plays an active role in updating Australian standards for earth-retaining structures and bridge design. Please join me in welcoming Dr. Min Tsai.
I would like to thank Engineer Australia and Brickworks for the opportunity to share and communicate with each other. I think my presentation will more focus on the embedded retaining wall and particularly relating on the design, technical details relating to design. So my presentation will include the contents are like historical review of embedded retaining wall design, lessons learned from deep excavation failures, mainly from Nicole Highway, and based on the above, we will see how these lessons learned can be incorporated in Australian standard and the relevant design considerations to be considered by a geotech engineer to perform the embedded retaining wall design. Next, yeah. So generally speaking, a retaining wall, any type of embedded retaining wall design will have two sets of analysis. The first set will be for ULS analysis using limited equilibrium method so the only purpose is to determine the minimum embedment necessary to achieve equilibrium. Then after we have the minimum embedment, that will be used as input to carry out the second set of soil structure interaction analysis to determine the relevant action effects like bending moment, shear force, and strut prop forces, which will be subsequently used for structure design, and the wall displacement used for serviceability limit state. So the embedded retaining wall design, particularly the UAS analysis, does have a long history. So I try to summarize that in a table format so everybody can, hopefully that's easy for everybody to have a look and appreciation. So I will focus on the two categories, the methodology of analysis and the design philosophy. So the first column is about the relevant documents listed in the order of years. I'll come to the methodology analysis first. I think for any geotech engineer who got the experience of design embedded retaining wall must be familiar with the terminology like CB2, Bell-Ports method, BSC method. But it's very interesting to note here, when it comes to the recent design codes and reports, documents, all these conventional methods have disappeared. So the key word has become something like achieve equilibrium. So that from design philosophy point of view, I think it has gradually evolved from the traditional overall factor of safety method to the strength reduction factor method or resistance reduction factor method. I will dig a little bit deeper into the methodology analysis. I take cantilever as one example. Cantilever basically 100% rely on the depth of embedment to achieve equilibrium, to achieve stability. So, so basically the failure mode is against a point that is close to the pi top, that generally referred to as the pivot point. So below and above that point, the KKB change directions. So this is a theoretically correct approach. We've got like two equations. Then we can determine the where the pivot point is and where the par tau level is. But unfortunately, this analysis itself is quite complex. That has left the room for the simplified approach like a CB2. So CB2 method has been like first proposed in serial report 104. Is not a complete equilibrium. I will show it later in the next slides. So the bending moment is at equilibrium, but shear force is not. Serial report 760 have a bit more details about this methodology. So basically, the principles are exactly the same. Two equations, two unknowns. The unknown for the cantilever basically is the pivot point and the par tau level. So I won't go to details of that. So anybody interested, you get interested, you can have a look at the serial report. Serial report also have a section for the single propped walls. So basically, the principle and the approach are exactly the same. Two equations and two unknowns, but this time the unknown become prop force and the embedment. This make the calculation much simpler, because if you take the bending moment against the physical support point, you only have one unknowns left. So I just want to show something visually by some charts. Hopefully that is easier for everyone to have appreciation. So I have come up with a work example using CB2 method that is clearly shows the bending moment is not equilibrium for shear force. As illustrated in serial report 104, it says to cater for this incompleteness, a 20% increase of the calculated embedment should be increased. I also have done a full equilibrium method. You can see that both the bending moment and shear force are at equilibrium. So the calculated embedment can be used as the final design value. So I would like to wrap up the methodology using this by by comparison the results from different methods. So you look at the red dot line is the total level from CP2, blue from Berlin ports, and the green from the equilibrium. I think that also partially explains why the convention methods like CP2, Berlin ports, and the BSC, were never mentioned in the recent design codes, because I think the equilibrium is, in my opinion, is a better option because it is theoretically sound, it mathematically complete, and it's also in line with all the recent international standards and Australian standards. Then on top of that, it can let us have a more economical design. Another important ULS failure mode is the piping resulting from the seepage. So I have shown some like theoretical background. So that says if you have any water height difference in soil, you will generate a seepage. So this seepage, the seepage force is in proportion to the hydronic gradient. Another important factor is how much hydronic gradient can be taken by a soil. If you look at this, the equation they call ICR, it's interesting to note this ICR is something similar to the submerged density. So the fact safety is just defined by the ratio of the I critical to the I exit. This is what I have extracted from BS802. It shows how to calculate the water pressures, including seepage. This is the design requirement as illustrated in Eurocode. It's interesting to note that the equations shown in Eurocode are the same as the theory. Because if you look at the equation in Eurocode, the ratio of gamma dash by gamma W is actually the ICR. D divided by delta H is actually the I exit. So Eurocode has also given some partial factors for design. It's 1.35 for unfavorable and 0.9 for favorable. It is equivalent to an overall factor of safety 1.5. So after these two overall requirements, we come to a bits and pieces for the calculation itself. I think the first things we need to calculate normally is the K and the KP. So I think people I either use a Rankine method or Coulomb method to do the calculation. So here I would like you to draw attention to what has been described in serial report 760, chapter 4.1.3. Basically, it says Rankine method could be too conservative. Coulomb method could be unsafe. So, but the recent theories, like what I have shown here, give accurate values of the limiting lateral stress for use as a basis for design. This has been used in Eurocode and in some commercial softwares like WALAP and Geo5. These are the equations incorporating this recent theory. I won't go to details. If you are interested, you can have a look. Another important design consideration is the tension cracks. We all know if we use a high C dash value, the top portion of the retaining wall will be subject to nothing. But the code does not want you to do that. It has introduced a concept like MEFP that stands for minimum equivalent fluid pressure. So if water is expected on the site, then you have to consider the scenario, the tension crack could be filled by water. So you have to use minimum pressure. Your MEFP should be like 10 times Z. Even water is not expected, you still have to use a minimum MEFP is equal to 5Z. That is almost equivalent to a Ka value of 0.25. BS802 has a slight different methodology to deal with the tension crack, but whatever it is, you still have to take the MEFP. You still cannot allow portion of the retaining wall subject to nothing. Another issue is the compaction-induced pressures. We have seen some reports about the retaining wall collapse associated with this kind of pressures. So I think the message is very clear. So if you haven't considered that compaction-induced pressures, you have to make it clear in your report. Maybe you also need to put some control measures in place on drawings, something like lightweight handheld compact has to be used with a certain clearance from the wall. Basically, you do what you say what you do. So after all this review, I would like to have a look at what has been included in the current Australian standard regarding the embedded retaining wall. It's interesting. There's only one place in the current Australian standard, that is it's in Appendix E. It says where retaining walls using embedded parts are adopted at a site, the design of such structures should be carried out as suggested in AS 2159 for laterally loaded parts. You know, AS 259 is a pioneer design code. I don't think this approach is a correct approach, but how much it can be go wrong. So I have done two analyses. So the left one is the sort of like the prop limited equilibrium method for retaining wall. The right is the lateral load part. So this shows the shear force diagram. You can see the shear force are the same at excavation level. However, the maximum shear force are significantly different for these two cases. The next slide shows the bending moment diagram. So again, the bending moment values are the same at the excavation level, but the maximum values are significantly different. It just simple tells retaining wall design is a retaining wall design. It's not like a lateral load part design. So after all this, I would like to share some lessons learned from Nicole Highway collapse. Why I have selected this collapse area? Because I have been heavily involved. Also, there has been extensive forensic analysis by many experts representing different organizations. So basically, this is a collapse area in relation to the subway system at that point of time. Google Map view, showing the location. Another photo showing the location in relation to the surrounding buildings. I just would like you to bring your attention to this collapse area. Is very close to the river. This is roughly the extent of the collapse area. It mainly occurred in type M2 and type M3 area. So these are the typical cross sections in that two areas. So basically, that is a very deep excavation, more than 32 meters. So with two diaphragm wall propped by 9 layers of stratum, with two JGP JGP slab. The top JGP is called the sacrificial JGP slab because it will be demolished and removed when the excavation progresses. This is what the site looks like before collapse. The propping system in the area, excavation in progress. This is the very moment of the collapse starting, caught on camera. That is occurred around 3:30 in the afternoon on 20th April 2004. A few minutes later, the the twisted propping system in the collapse area. A comprehensive monitoring system was in place before the failure. It helped us to see the behavior of the retaining wall system. So these are the two readings from 2 kilometer readings. So this red dot line is the trigger level. The purple line is the design level. As you can see, these 2 levels have been far exceeded 2 months before the collapse. Also within that 1 week, 1 week leading to the collapse, if you see here, so actually we see a sudden increase of wall deflection. The strut force have been also were monitored on a real-time basis, so it captured the strut behavior to the last moment of the collapse. So actually you can see on the day of collapse, the strut line has become ineffective. They start to shed the force to its upstrut, that is strut 8. So that's why you can see the strut 8 forces have got a very abrupt increase that has far exceeded the design capacity. Yeah, that is the Weyler strut connection that has buckled in the morning of the collapse. So after the collapse, I think everybody want to know what are the real causes. So LTA has set up a recovery team. I got heavily involved with that type of work. So the first thing brought to our attention is that geometry in the collapse area. So if you can see the geometry, even you are not an engineer, I think probably you could say something is not very right, because the excavation is more than 33 meters, but the embedment is only a mere 4.9 embedment. So after rounds of discussion with the contractor consultant, so we decided to do our embedment checking independently. I think about 1 week later, we came to the same conclusion: the embedment is not adequate. I also have redone this analysis recently by putting it in a coding. So the right one, the right figure is the result. So just in order to achieve a bending moment equilibrium, we need a minimum required embedment of 15.21 meter compared to the actually installed 4.9 meter. That is basically actually is 3 times more. To make things worse, even with that 15.2 meter embedment, so to make things worse, so when even with that 15.2 meter embedment, we have another checking for the piping. We found that fact safety is 1.03, is far below the required fact safety 1.5. So you can see that the embedment is just 2 liters. So all the experts, they have done extensive forensic analysis. I think all the experts have unanimously agreed that the method A in practice adopted by the contractor is not good. So basically, it overestimates the soil strength and underestimate the wall bending moment and the wall deflection a lot. Also underestimate the strut forces. Then all the experts also unanimously agreed the trick starts from the failure of the connection between the last strut and the Weyler. The original design looks like this, with with a steel plate stiffener. But even with that, plate stiffener, some of the balcony have been observed in some of the areas. I'm not sure whether it's in the collapse area or not, but some balcony have been observed. But it's very fortunate when we come to this collapse area. I think several days before the collapse, the contractor realized they have used up all of the steel plates, but they have got some C-channel in place. So they then propose to use the C-channel to replace the steel plate. This is what it has been actually installed on site. It's really unfortunate. So on the day of the collapse, a balcony has been observed between the connection between the strut and the weather connection, and a sway movement has been observed in the morning of the collapse. So this has been also well caught in the strut force monitoring. Subsequent review by LTA, has showed some more substantive connections, like the connection between the struts and the kim posts. So the purpose is to reduce the effective length of the struts to make them work more efficiently. So basically, this is like so you look at what has been required and what has been installed on site. So obviously, the connection installed on site is substantial. It could reduce the strut capacity significantly. Okay, another contributing fact of the site is actually the construction site is located on the reclaimed land, and the monitoring shows the consolidation was not completed yet at the time of collapse. That could weaken the soft marine clay further. A late three-dimensional analysis shows the curving diaphragm wall in that area could also play a role to contribute to the collapse. So after a very lengthy and expensive court case, the case closure by state prosecution. So the things we learned from this collapse, like the UAS analysis, including the piping, it must be performed to determine the minimum required embedment. Then FEM software should never be used like a black box without sound engineering judgment. The over-reliance of design decisions on FEM analysis must be discouraged, and the basic mechanics like engineering principles must be employed to check or verify FEM results. Steelwork connections details must be done and reviewed by competent persons. Design is not a one-time act, but a continuing process of ensuring that the design assumptions are consistent with reality. So we come to our Australian stand. We try to reflect that experience and lessons learned as much as possible in our new Australian standard. So, for example, we have stated very clearly the UAS analysis, a set of UAS analysis must be performed. Thank you. Let's bring to the end of my presentation. Thank you.
Thank you, Dr. Min, for your input today. I now have the pleasure of welcoming our third speaker, Adam Ransley. Adam has a strong foundation in mining and civil construction, and he brings extensive industry experience to his role at Brickworks, Australia's leading brick manufacturer. He is committed to the company's forward-thinking approach and takes pride in Brickworks' ongoing commitment to strengthening Australia's building industry. Please join me in welcoming Adam Ransley.
Thanks for the introduction. I'm Adam and I'm from Brickworks Building Products and I manage our civil and landscaping market. So just an overview from today. There's 5 different topics that I'd like to talk about, with the first being types of retaining walls. Selecting the right type of retaining wall is critical to the success, safety and cost efficiency of any project. The correct wall system ensures the structure can safely manage soil loads, drainage, site conditions, preventing failures such as cracking, sliding or collapse. It also directs impacts of constructability. Choosing the right solution can reduce excavation, speed up installation and minimize disruption on site. From a commercial perspective, the right retaining wall balances upfront costs with long-term performance. An unsuitable wall may appear cheaper initially, but can lead to higher maintenance, remediation, or even complete replacement down the track. Additionally, selecting the appropriate system ensures compliance with engaging requirements, site constraints, and environmental considerations to reduce as much risk as possible. Getting the retaining wall type right from the outset protects the project timeline, budget, and structural integrity, making it a key design and planning decision rather than just a construction detail. So what are retaining walls? Retaining walls are essential structures used to resist soil pressure from residential landscaping to large-scale infrastructure projects. They are necessary because without them, soil will slide to its natural angle of repose, remaining unrestrained with reduced load carrying capacity. Retaining walls help craft and maintain land topography to our design needs, enhancing constructability and enhancing land value. Erosion is the natural process of soil, rock, and sediment displacement caused by wind, water, or human activity. In civil projects, uncontrolled erosion can compromise structural integrity and increase maintenance costs. It can lead to slope failure, sediment runoff, and damage to nearby structures or landscapes. Left unmanaged, erosion reshapes landforms over time, unacceptable when building long-life assets like factories or public infrastructure designed to last 60 to 100 years. Retaining walls help control erosion by stabilizing soil, reduce surface runoff, and supporting steep gradients. Usable land refers to flat, stable ground suitable for construction, access, or landscaping. Sloped or uneven terrain often limits functionality and development potential. By transforming steep gradients into level surfaces, site usability can be significantly increased. If you look at the image, by building retaining walls, a flat surface is obtained and a space of sediment basin is created in front of the wall. Retaining walls play a key role in the process by creating stable, buildable platforms on challenging terrain. Use Sydney as the example. We need these walls to unlock the potential for the future developments. Enhanced landscaping involves shaping and optimizing outdoor space for aesthetics, function, and long-term stability. It often includes terracing, defined planting zones, and leveling pathways or recreational areas. They enable precise elevation control and clean transitions, which are critical for achieving high-end landscape outcomes. Retaining walls support the features by holding back soil, creating flat surfaces, and preventing erosion. Even though they are often seen as aesthetic features, landscaping walls still perform critical structural functions and must meet the same durability and stability requirements as a permanent structure. Product overview. Product quality is essential in construction market. It directly dictates customer satisfaction, brand reputation, and long-term profitability. High-quality products create trust, they differentiate brands in crowded markets, and foster positive word of mouth, while poor quality leads to wasted resources and lost customers. So which product is best for a retaining wall? The options are a cantilever, mass gravity, and soil reinforced retaining walls, which differ mainly in how they resist soil pressure. A cantilever retaining wall uses a reinforced structure with a base slab that transfers forces into the ground, relying on both the wall and the height of soil above the base and stability. A mass gravity wall resists pressure purely through its own weight, making it thick and heavy, but in simple in design. A soil reinforced wall strengthens the soil itself using layers of reinforcements such as geogrids, allowing the soil and reinforcement to act together as a stable mass, making it efficient and flexible for taller structures. So some of the options are masonry grey blocks. A cantilever masonry block retaining wall may appear as a simple landscaping element, but they function as a structural system relying on base footing, stem, and heel stability. These walls must control movement, preventing overturning and sliding, and maintain alignment under varied load conditions. Cantilever walls rely on a combination of reinforcement and in-situ concrete to achieve structural performance. Reinforcement bars are placed vertically and horizontally with high-strength concrete routed inside the hollow blocks, forming a complete structure. The blocks act as a permanent framework, available in different colours and finishes, adding aesthetic value while concealing all structural components. Another option is dry stack retaining blocks. Modular blocks are gravity or reinforced walls built using dry stack interlocking concrete blocks. These blocks rely on their mass, interlock, and when required, geogrid reinforcement to resist soil pressures and maintain stability. Heron, Sydney stone, and keystone fall into this category. They are widely used in residential, commercial, and infrastructure projects due to their versatility and ease of installation. Modular blocks are available in various sizes, colours, and textures, making them suitable for both structural and aesthetic applications. The system is dry stacked without mortar, allowing minor flexibility and sediment tolerance, especially on expansive soils or curved alignments. Concrete slipper retaining walls. Concrete slipper retaining walls are a popular modular system used in both residential and civil applications. They consist of precast concrete sleepers inserting between steel posts, relying on post embedment and sleeper strength for overall stability. Despite their simple appearance, they are fully engineered to resist lateral earth pressures and are suitable for both cut and fill scenarios. Concrete sleepers are reinforced with internal steel and can be manufactured in a wide range of finishes, colours, and textures to suit project aesthetics. Steel H and C section posts are typically hot dip galvanized for corrosion protection and structural performance. Concrete sleepers offer superior longevity, immense structural strength, and high resistance to rot, termites, and other situations such as fire compared to timber. They are low maintenance, preventing warping or splitting, and often modern aesthetic options. While initial cost and installation can be higher, the durability offers better longer-term value. Mass gravity. Large concrete retaining walls use heavy-duty blocks designed for gravity or reinforced applications. Systems such as Key Mass, Ready Rock, Vertiblock, and Magma Stone fall into this category. Design considerations. I just want to highlight a case study regarding a concrete slipper retaining wall. During a construction of a retaining wall, an issue arose where the installed posts were found to be inadequate in length for the actual wall height. The posts had originally been designed and ordered based on the conveyancing provided data, which was later identified as inaccurate once the site conditions were confirmed. As a result, the installed post did not achieve the required embedment or structural capacity, creating a risk to wall stability and compliance. These presented a significant challenge due to the high cost and long lead time associated with procuring replacement posts. The situation required immediate reassessment of design assumptions, coordination with the stakeholders, and exploration of alternative solutions to minimise project delays and cost impacts. Case study number 2. During construction, an issue arose when service mains were found to be installed in incorrect locations, conflicting with original retaining wall design. The wall had initially been specified as a concrete sleeper system. However, the rigid design did not allow sufficient flexibility to accommodate the required service connection. To address the problem, the design was modified to a keystone retaining wall system, which provided greater ability for adjustments around the service mains. The change enabled the integration of the 2 service connections while maintaining structural integrity through required redesign, coordination, and adjustments to construction sequencing to minimise delays and additional costs. Why Brickworks? 100% Australian owned with manufacturing facilities across all states. We have a strong focus on sustainability and continuous operational improvement. At Brickworks, we've made significant investments and set ambitious targets to further reduce our environmental impact. And we're passionate about collaborating on your projects, learning your vision and bringing them to life. And our team is committed to supporting you every step of the way. At Brickworks, our focus is creating beautiful, durable products that stand the test of time. They're globally recognised as a leader in quality building materials with brands that lead through style and product innovation. We're an active member of Australia's vibrant design and construction community, and we value ongoing collaboration and dialogue. Your feedback helps shape the development of new products and services, ensuring we continue to meet evolving design and performance needs. At Brickworks, we're dedicated to building a greener, cleaner, and more sustainable future. Since 2006, we've achieved a 56% reduction in Scope 1 and 2 emissions across our Australian operations. We have a target of a further 15% by 2030. Currently, 12% of our manufacturing energy comes from renewable sources. Brickworks is the trusted partner to deliver superior quality and product availability for good value, so you don't have to worry about the risk. Thank you for your time. I look forward to working with you in the future. Please reach out if you need any help.
Thanks, Adam. Well, now it's time for our audience to get involved. So a big thank you to everyone who has been submitting questions. I've been keeping an eye on the chat box. Questions have come through, so let's jump straight. We received live today came through from Jack. Now, Jack's question, maybe a couple of you may be able to respond to this one, but I'll kind of go with kick us off. How widely are concrete sheet piles used in the Australian market?
Hi, Megan. I'll answer that one. So I think they're referring to more the sheet piles, and where we see them typically is around the seawalls and the flood defence, water control. These are usually temporary retaining wall system. It's not usually there for aesthetics looks, so usually you see them as a temporary sort of solution.
Awesome, thank you. Now, I'll jump around to a few different questions that we had coming through, and I saw, Tan, there was a question for you, and it was came through from CGEM 1988, and the question was about what about walls on boundaries? They have been asked to design and certify walls 400 millimeters high.
Yep, I've done some walls in New South Wales, which need certification up to 600 mil anyway. Bear in mind that certification, whether it's a 400, 600, 800, it all goes back to the state building regulation and acts. But the Australian code for retaining wall is very clear that if it's less than 800, you do not need to design to meet the Australian standard. But some building code in each state varies, and they might put a condition to say that, look, if you design 600 or 400 meters, you might need to design to Australian code. So it is best that you check with your building certifier, what does the actual building code of that state says anyway, okay?
Awesome. Thank you. Min, I'll bring you into the conversation. We had a question come through, and I'm hoping that you'll be able to answer this one. It was around how to design a series of step retaining wall.
Sorry, a series of
Step retaining wall was one of our live questions that came through.
Sorry, could you please repeat that question again?
How would you design a series of step retaining wall?
Yeah, I think it's tier. Yeah, I think we could talk about like tier retaining wall. I think it is a bit tricky because of the interaction between the because the front and the back wall. So normally, you know, because we have this question with Qiming. So normally you can design your the sort of like the back retaining wall or the up tier retaining wall, you know, to ignore the contribution from the front row. So to make sure, you know, that is safe, because yeah, then after that you still need to put that derived geometry put into SL, you know, to put like SL soil structure interaction analysis to get the deflection, you know, to look at the results. I mean, yeah, it's a bit tricky for the UAS analysis because of the complexity between the front and the back retaining wall. Jimmy, do you have something to add?
From myself, or did the other speakers want to add to that answer?
I'm same to the same person anyway, that same question. Tier walls is normally the separation, right? If you follow the council standard on tier walls, they prefer your separation to be quite far apart, where you can design the tier wall independently and upper wall and lower wall. But when it comes too close, that's where the complex calculation comes in. What I've normally do, as I say in my previous slide in the webinar, I say that I'll treat the upper wall as an independent wall, and then design from the top of the wall to the base of the bottom of the wall where the soil is, and the lower wall I'll treat it just like a normal wall. So in the event of any removable wall at the lower area, right, the upper wall is still standing, because what is most important is to protect the upper wall. That's the most important thing, because the chances of removal of a tier wall is always at the bottom wall. Someone will just remove it, but if you remove it, the wall is still standing. But if you really want to do a real calculation on it, you will just have to use a soil structure interaction program like Plexus. So normally what we do is do an approximation of the pier depth on the upper wall and the lower wall, and then you input into your Plexus and you do your analysis as a starting point, and then from there you just do your analysis, get the bending moment, the shear force, and the embedment depth, so that you get the factor of safety that you require. Look, most infill and brownfield structural engineers are not geotechnical engineers. They do not do Plexus, but is the set point is to say that when you do embedment wall, you have to do a serviceability check, and that serviceability check is only be able to use a soil structure interaction program. It will be painful, but this is where the expertise of the geotechnical guys comes in. and you will have to use a geotechnical to do the analysis for you for serviceability.
So Tan, going on from that, one of the questions that came through from registration was around what are the most common instruments to monitor retaining wall structures. That came through from Juan Valero. So just if you wanted to maybe comment on that one.
Which one is it? Yeah. Go ahead.
It was, what are the most common instruments to monitor risks in retaining wall structures? It came through through the questions we received on registration. I can move on to another question if you like.
Getting out on the site, making sure that the retaining wall is built to spec, and monitoring the progress of that throughout the life. There's a lot of times where in our field where we get the design and it comes through, and what they actually build versus what is designed could be chalk and cheese. So I think it's making the effort to get out there and making sure that the retaining wall is built to the spec. And if there is changes, recording that and updating the drawings to make sure that the process is followed.
Awesome, thanks Adam. I'll move back to the question that we received live. We had a question which came through from Zachary, and I'll direct this one to you, Tan. It was around Form 1512, so specific to building elements, which civil don't typically certify. Zachary was keen on your thoughts.
All right. Okay, that's good question, Zachary. Very good question. A civil engineer will never certify or will never issue a Form 15 or Form 12 for a wall. Normally, it goes back to a structural or a geotechnical. But as I mentioned in my webinar, a wall consists of 3 disciplines. Okay, so the civil engineer, when you draw your wall on your drawings, you are taking a responsibility to say that you are actually wanting a wall to be built there. It's in your drawings. So when it's in your drawing, it is actually your design, and you will have to make sure that that wall, which is now a building product, you will have to do part of the certification. Now, your part of the certification will be related to your civil component. So if you are the main project consultant and for a subdivision, then what you have to do is just got to make sure that the structural and geotechnical engineers all will issue you the right certification form and given to you. And what you can do is you can prepare. You don't have to sign a Form 15 or Form 15 or Form 16. You just prepare a certification as a civil engineer to say that all the walls has been designed and has been certified by the relevant discipline, and you yourself will then put in that letter as in the certification to say that you have checked all the drainages. Because bear in mind, a wall in AS 4678 in Chapter 5, there is a drainage component. So when there's a drainage component in that code, it means that watch out. You have to design a drainage. So who is responsible for the drainage? So it has to be a civil engineer to look at it. And you just got to make sure that all these are met, and you then do your certification on the letter and you just give it to the authority. That's what the civil engineer should do, and as a project consultant.
Awesome. Well, look, last question for today. So we had so many questions come through with registration and live, but this will have to be our last question. when is global stability required to be considered? So I think, Tan Ching, you've got the final question. When is global stability required to be considered?
Okay, good question. Now, normally when the wall is is high, I normally do when anything more than 3 meters and above, whether it's the wall is sitting on the flat ground or on the slope, more than 3 meters, I will normally ask a geotechnical to do analysis anyway, to do a global stability analysis. But if the wall is being built on an angle of a slope, and whether is it forming a natural slope that's retaining a natural slope, or is it a backfill slope, up to a certain angle of angle of the slope, I will normally ask for global stability. But bearing in mind that councils nowadays, they will always write a condition in your development application approval and say that you need to do a global stability to meet the factor of safety 1.5. For very reason is because if you look at the overlay of council, if your land that you're building your wall is on a landslide risk overlay, then you will have to do a global stability. If it's not on a landslide overlay and the wall is still high, I will still do a global stability. I will normally 3 meters, I will do it. I wouldn't take any more risk because I've seen that failure before anyway. Look at some of those photographs anyway. Because grounds condition varies, so it's best that global stability be taken into account.
That's all the time that we have for today. So please join me in thanking our Dr. Min Kai and Adam Ransley for their time and input. I do know, reading the chats, that our audience have loved the presentations today, the detail that you've all provided. So a huge thank you to you all. I would like to obviously thank Brickworks for their support. Now, if you don't mind completing a short feedback form, which is in the description box below, as you know, it really does help us improve and plan future session. Audience, if you could complete that, that would be great. And also, please scan the QR code if you to register for more events and which are upcoming. So yeah, please click on that QR code. Really important that you do that today. But look, my final comment is a huge thank you to you, our watchers. Thank you for watching us, and we hope to see you at our next Industry Partners event. Good afternoon, everyone.